Hello YouTube, this is Eric from Coder Snacks. Today, we're going to talk about linked lists. Let's get started. Warnings in advance, I'm going to rant a bit in this video. I believe many linked list problems are inappropriate for interviews and linked lists in general are overused. Why? First, most linked list problems in the interview repertoire are poor questions. They're things that don't happen in real linked lists, or are contrived examples that are things we should fix in underlying implementations, not work around. Next, great interview questions are based on real-world problems that can be worked out if we have a solid grounding in computer science, even if we've never heard the problem before, and they let us demonstrate real, useful skills. The idea is to see how well we reason, think, and work. It's not a good test if it's a gotcha, or the problem is unrealistic. One of these commonly asked problems was an open problem in CS for years. How realistic is it to solve it in 35 minutes if we haven't heard it before? Finally, in CS curricula, we learn that insert on a linked list is O of 1 and insert on an array is O of n. This is true, but when we see that, the implication is lists are far worse, and that's often not the case. Constants matter. We'll talk about this more in the video. Poor though they may be, these problems are out there, and they get asked a lot. Many interviewers consider linked lists to be a good way to test pointers and indirection, but these problems are so commonly asked, and some involve such leaps to solve if we don't know them beforehand, that often all they test is whether someone has studied the problem before. And so today, we're going to briefly cover 4 commonly asked linked list problems to familiarize you with them. There will be less code than usual, and there will be less explanation of thought processes, since these mostly just involve knowing some trick. I don't usually recommend memorizing solutions to problems, but for these, just make some flashcards. First, what is a linked list? Even if they're frequently misused, we should understand what they are. A linked list is a collection of elements, or nodes, tied together by pointers. Each element has a value and a next pointer, which says where the next element is in memory. In Python, we can do this by storing the next node object. The last element of the list will have its next pointer pointing to none, which indicates the end of the list. This structure, where we only have next pointers, is the simplest kind of linked list, called a singly linked list. We'll also have a value containing the head node, or the first node in the list. From the first node, we can traverse the whole list using just the next pointers. Here's some sample code. The linked list object just stores the first node, and the nodes themselves contain a value and the next node object. It's possible to have another pointer that points back to the previous element, letting us quickly move backwards or forwards in the list. This is called a doubly linked list. Most interview questions assume a singly linked list, but you should clarify this if you're asked a linked list question. With both of these, adding a node is O of 1 if we have the node we want to add it to already. Let's go back to our singly linked list. Let's say we already have the 22 node and want to add a node with the value 10 in front of it. We make the new node with the next node pointer set to 22's next 24. Then we take 22's next and point it to our new node, and we're done. This takes O of 1 time. In contrast, a Python list is backed by an array, and when we insert into the middle of it, we have to move everything after our insertion point over. For example, let's say I want to add a 20 to this sorted list. Assuming I know where to insert it, I have to move everything above 20 over to make room for the 20. This takes O of n time, where n is the size of the list. The same thing happens for deleting an element. We have to scoot everything back over. Additionally, even in the case where we're always adding to the end, such as a stack or queue, sometimes the insert on the array is O of n. In a linked list, we simply make another node and point to it, which is O of 1. But a list is backed by a fixed size structure, and sometimes we'll be out of room. To append, we'll increase the size of the array by some amount depending on the implementation of list, and copy our list into the new array. This is also O of n. In the worst case, inserts on a list, even at the end, are O of n. On average, adding to the end of the list is amortized O of 1, but in the worst case, on an individual item, it's O of n. Of course, there is a disadvantage to linked lists. If we want a middle item of a singly linked list, we have no way of accessing it directly. We have to start at the head and go next repeatedly. Finding an arbitrarily indexed node in a linked list takes O of n time, but for a lot of applications, we don't really need to do this. Anyway, insertions and deletions in O of 1 instead of O of n. Linked lists seem like the way to go, but not so fast. First, even if we're inserting into the middle of a list a lot, the penalty may not be as great as you think, because memory copies can be very fast. They can be done pages at a time, so moving these n elements might only take one step. Second, lists are backed by arrays which have cache locality. Without going too deep into this, here's a representation of a list in memory. When we access a piece of data in memory, it takes differing amounts of time depending on whether it's stored in a memory cache. When you read a piece of data, it's common to also read blocks of data near what you requested, because you're likely to request something nearby next. But with linked lists, nodes could be anywhere in memory. When we get an element, the cache still loads nearby memory, but the next element might not be loaded in. This means next on a linked list can take much longer than next on an array. Finally, even if we're sure we want a linked list, we should use Python APIs when possible. If we're certain we need this, use collections.deque, which is implemented internally using a doubly linked list. Don't roll your own. I'll put some links in the description, but here's the takeaway. Don't optimize prematurely. There are good uses for linked lists, but in general we should use a list until we know we have a performance problem and no list usage is causing it. Now that we know about linked lists, let's talk about linked list problems. We'll cover 4 of them today, and number 1 is reverse a linked list. If we look on interview sites like Glassdoor or CareerCup, this is one of the most frequently asked interview questions, and it's worth preparing. Here's our linked list again. We want to turn this linked list into this. There are 2 main ideas to remember here. First, for each node, we need to change the next node field to point to the previous node, which we don't have a link to. As we go through the list, we need to hold on to the previous node so that we can link to it later. Second, once we change the next node to the previous node, we no longer have a link to the next node. We need to keep a copy of that next node before we make the swap. We'll go through repeatedly getting the next node, then switching our next node pointer to the previous node and our previous node to the current node. Here's some code to do it. We start by setting our previous node to none, which will be the new end of the list, and our current node to the head of the list. Then, while we haven't reached the end of the list, which is a none, we get the next node first. Now we have all of our previous, current, and next nodes. We set our current nodes next to the previous node, reversing it, and advance our previous and current nodes. We then repeat, getting the next node from our new current, and so on. At the end, we set our new head to the previous node. Current now points to none, so we want the last node that was actually a node. The main trick to this problem is making sure we don't throw away access to nodes we need. More rarely, an interviewer will ask you to solve this recursively. I'll put some links in the description for that kind of solution. Moving on, question 2. Detect a cycle in a linked list. What does it mean to have a cycle in a linked list? Take a linked list and imagine we change a next pointer to point to a node that is already in our list. That creates this structure, and we can no longer reach the end of the list from the head. This list goes on forever. I'll put a link in the description why this is a question an interviewer shouldn't ask, but there are 2 main points. First, realistic linked lists don't get cycles. Linked lists have push or insert methods that take values, not nodes themselves. If our API is designed correctly, we won't get cycles, and if someone is messing with the internals of our class and they manage to get a cycle, they kinda deserve what they get. Second, the real answer to this question is an aha moment. A reasonable first idea would be to scan through the list, put each item in a set or something similar, and see if we have a duplicate. If we do, we return true, there's a cycle. Here, we'd add A through F into our set, and when we go back to C, we'd see it's already in the set, and we return true. But then the interviewer will say, great, now do it in O of 1 space. And now the aha begins. In the 60s, this was an open computer science problem. If we haven't seen this problem before, they're expecting us to solve in interview time what used to be an open problem in CS. How awesome is that? Well, have no fear. Here's how we solve it. Take 2 pointers, a fast pointer and a slow pointer, and point them to head. Repeatedly advance the fast pointer 2 times and the slow pointer once. If there's no cycle, the fast pointer will reach the end of the list. But if there is a cycle, the fast pointer will enter the cycle and start going around it. Eventually, the slow pointer will enter the cycle, and each time through our loop, the fast pointer will get one closer to the slow pointer, and eventually they'll be in the same place. If our two pointers are ever equal, there's a cycle. The main trick to this problem? Use two pointers, one fast, one slow. Question number 3. Find the kth element from the end of a linked list. The straightforward answer is to iterate over the list once to see how long it is, or use something like len if your class implements it. Then, knowing how many elements there are, iterate again, going the appropriate number forward, something like n-k depending on how we define the kth element. For example, let's say we want the third element from the end of this list. We iterate through it and find there are 7 elements. We need the fifth element, 7 minus 3 plus 1. We can iterate 5 from the head to get that element. This takes O of n for the first pass, and O of n in the worst case for the second pass, and O of 1 space. Many interviewers dislike this solution and instead prefer a recursive solution which takes O of n time and O of n space on the stack, or a solution that doesn't loop through the list first. The answer they're looking for is as follows. Set one pointer to the head, and then advance another pointer k-1 nodes. Then advance both of those pointers one at a time until the pointer in front reaches the end of the list, and return the value of the behind pointer, as we show in this example. What's silly about this solution is that it does the exact same amount of work as the straightforward answer. In our first one, we loop through the whole list once, then forward n-k steps in a second loop. In this solution, we have 2 pointers in the name of cleverness, but one of them advances through the whole list, and one of them advances n-k nodes. Both solutions are O of n and are completely equivalent. The straightforward answer isn't clever, but cleverness isn't necessarily a virtue in coding. The recursive solution takes O of n space on the stack, which means we can only use it for small lists. We should use the straightforward solution since both approaches are O of n time and the iterative solution is O of 1 space. Interviewers, take note. If you want to test a candidate's knowledge of recursion, there are tons of good recursion problems out there. Take any one you want. Anyway, the trick to this problem is using 2 pointers again. Question number 4. Given 2 linked lists that converge, find where they converge. This is a more reasonable problem in the sense that we can reasonably work this out at a whiteboard, and there are some nice small hints you could give. It's still the kind of problem that should never happen in practice. What does it look like when 2 linked lists converge? At some point, the next nodes for 2 lists with different heads have next pointers that both point to the same node, where they converge. For example, here are 2 lists with heads A and B that both converge at C. From that point on, they're the same list. Given the heads of the 2 linked lists, how can we find this spot? There's an O of nm brute force solution, but we can do better. First, check how long the lists are, which takes O of n plus m. Then, note that at the spot of convergence, we'll be at the same distance from the end on both lists. Great. Start with 2 pointers at the head of each list, then move the pointer of the longer list ahead until both pointers are at the same distance from the end. For example, here, A is 7 elements and B is 5 elements, so we move the A pointer ahead 2 elements. Finally, move both pointers forward repeatedly until they're equal. If they're never equal, the lists don't converge, but if they are, we have the point of convergence. The main trick on this one is moving our pointers to be the same distance from the end. And there we go, 4 common linked list interview problems. These get asked a lot, and you should familiarize yourself with them. Not because they're great questions, but because you want to know them in an interview. I want to leave off with some final remarks. First, there are cases in which a linked list is useful. I don't mean to say that it's always bad to use linked lists. For example, sometimes the O of n resize of an array is not acceptable in a performance-critical situation. Or we might be implementing something like a least recently used cache, where we're using the linked list in conjunction with some other data structure to achieve some effect. The point I want to make is, don't optimize prematurely, and don't optimize for the wrong things. Optimizing for theoretical time complexity is not always the correct solution. Sometimes using a simpler data structure makes for more maintainable code, and code being imperceptibly slower is acceptable. Second, if you're in an interview setting, don't get into an argument with your interviewer about this. Don't try to convince them that you should solve the problem with a list or that their problem is bad and they should feel bad. Do your best to answer the question they're asking, and then, when you get the offer, evaluate what you thought of the interview process and whether you want to work there. After these 4 problems, here are a few more challenges you could try. Implement the 2 iterative algorithms we discussed recursively, which are reversing a linked list and finding the kth element from the end. Implement at least recently used cache. Finally, read some of the links in the description, particularly the one talking about linked list efficiency. Next time we're going to do a search problem. Given 2 words, find the shortest chain of words between the 2 where each word is in the dictionary and there's only 1 letter difference, add, remove, or change, between each word in the chain. I hope you got something out of this video. If you have any questions, comments, something I've missed, problems you want answered or covered, or just disagree with me about the power and beauty of linked lists, let me know in the comment section below. And if you enjoyed this video and want to see more, it would be great if you liked the video, subscribed, or both. I really appreciate it. See you here next time on Coder Snacks.